Hey Mustangs, in this video we're going to take a look at population genetics. Now up to this point we've taken a look at evolution or change in species and in populations, and we've focused on the environment and traits. So the biggest idea, the biggest things we know at this point is that if the environment changes, it's the organism's phenotypes, their physical traits that determine their survival. So what we're going to take a look at now is the genetics aspect of this, because we know that phenotype is connected with genotype. Your genotype determines your phenotype. But in the case of natural selection here, we focus solely on the fact that it's your phenotype that determines your survival. So we're going to see the connection here between phenotype and genotype now. So with population genetics, one of the first things we need to understand is the bell curve. Okay, so taking a look at this, if you looked at an entire population or entire species and you mapped them out based on a trait, any trait that you choose, you're going to find that most organisms in the species are going to fall into an average, that the most within a species is going to be at a certain range of a trait. And as you move away from the average, you find less and less organisms that have different variations of that below the average and different variations above the average. So let me go ahead and explain that. So let's say we're looking at crocodiles here. So in this population of crocodiles, when they're all full grown, they are not going to be the exact same size. Okay? So if we were to actually map them on a graph to look like this, so I'm going to go ahead and set up my graph here. On this side will be the number of crocs in the population that are a certain size, and over here will be the length. Okay, so let's say here we're starting with 0. And since we're focusing on the length, this will be the number. So as we go up, that's more and more crocs that are a certain length. So over here, I'm going to go ahead and put 5 feet, 10 feet, 15 feet, 20 feet. Okay. So if this is a population of saltwater crocs here, and we looked at them at adulthood, their full-grown size, we might actually find a few that are around 10 feet. Not very many, but we might find some. Crocodiles that are 11 feet, well, a little bit more than 10 feet probably, 12 feet, a little bit more, 13, 14. Until you hit 15 feet, you're going to see that most crocs would fall into the 15-foot range. And as you go above 15 feet, you're going to find less and less and less crocs that are these sizes. Okay, so if we actually connected the dots, you would actually see our bell curve. Okay, so the average of a species for any trait will find that most organisms within that species fall into that average. And as you go below average, you find less and less and less moving away from that trait. And as you go above average, you find less and less and less. Okay, so if it was the size of these crocs, the biggest that we find nowadays is about 20 feet, maybe a little over 20 feet. But most saltwater crocs fall into the 15-foot range, and some can even be as small, fully grown, at 10 feet. Alright, so what causes genetic variations? We actually talked about several of these. So genetic variations can be caused by mutations, can be caused by recombination. When we're talking about the gametes and everything, we're talking about crossing over, all those different things that we talked about with meiosis, and also the random pairing of gametes. Remember, all of your gametes, if you're female eggs, all of your sperm if you're a male, they are not identical to each other. Remember, they're unidentical haploid gametes. So depending on which gametes come together, it's going to form different possibilities. So you might remember this show here, John and Kate plus 8. If we look at their family, we look at the mom, the dad, even though they are all related, here's the mom, here's the dad, and here's their children, and here were the ones that came out, the sextuplets. If you take a look at them, they're not identical, even though, you know, they were all born at the same time. These 6 children here, they are unidentical. They're different egg, different sperm being used to fertilize the different eggs, and you have all these different possible traits. So we see even variation here, genetic variation within their children, and even though all 6 of these children were born at the same time. And then of course their 2 oldest daughters, still not identical. Alright, so let's take a look at gene pools and allele frequencies. Now, when we first learned about genetics, a lot of times students get confused when we say that, let's say like freckles are dominant to no freckles. And they're like, wait, how come there's not more people with freckles then compared to no freckles? There seems to be a lot more people with no freckles. Well, that has to do with the gene pool and what alleles are actually out there and their allele frequencies. So for example, let's take freckles. If we were to create a gene pool just based on freckles, we could actually do it for every single trait if we were able to identify what 2 alleles everybody has for their genotype. So what 2 alleles I have for freckles, what 2 alleles anybody else has freckles, and take it for the entire population. But let's just use freckles as an example here. All right, so if we created a gene pool, so here I'm just going to put a big old circle, represent a gene pool as if it was like a swimming pool or something. And we looked at everyone's genotype, and we put it all into one big pool here. Me, I don't have freckles, so I'm little f, and we took a whole bunch of people. We noticed that a lot of people are little f. Some people have freckles, they're big F, little f. So a lot of people, big F, little f. Some people are big F. But if we look at the overall gene pool, we can see that there's a lot more alleles for no freckles, the little f, and very few alleles for freckles, big F. Okay, so this is the gene pool in this case for freckle allele, the freckle gene. The allele frequency is how often an allele occurs. Okay, so the allele frequency for the no freckle allele is going to be much higher than the allele frequency for the freckle allele. So therefore, we'd expect to see more individuals with no freckles than we would with freckles, even though the freckle allele is dominant over the no freckle allele. Okay, so that's the gene pool here, and the allele frequency is how often a particular allele occurs in a population. Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium is a theoretical model, but it can be very useful for us to identify allele frequencies for a specific gene. So there's 5 conditions for Hardy-Weinberg equilibrium. If these 5 conditions are true, there would never ever be change in a population. And the good thing about this is if there's never any change, we can actually predict how many of a certain allele is out there in the population. Okay? So the 5 conditions are: there must be no mutations. So there can't be any mutations happening in a population. There can't be any immigration or emigration. So individuals can't leave or exit the population. The population has to be large, cannot be a small population. Individuals have to mate randomly. So regardless of how a male or female looks, they all have an equal opportunity basically. And finally, there has to be no natural selection, because what we've already seen so far with natural selection, that if the environment changes, individuals with the right traits survive, and that causes an overall change of the population. Well, that's change. And in Hardy-Weinberg equilibrium, the equal part, right? Equal stays the same. So in the equilibrium here, you can't have any natural selection occurring. All right. So here is the equation that can be really useful in determining allele frequencies, finding out how many freckle alleles are out in a population compared to no freckle alleles. Okay. But what the equation focuses on the most is the genotypes and how many individuals in the population are homozygous dominant, how many individuals are heterozygous, and how many individuals are homozygous recessive. Okay, so the letter P represents the dominant allele, the letter Q represents the recessive allele, and here is the equation that we're going to be looking at right here. P squared plus 2PQ plus Q squared equals 1. Okay, so if you take a look at this, I think the one that stands out the most, the easiest, filling into either one of these 3, which one do you think we would use to calculate how many individuals or what % of the population is heterozygous for a certain trait? Okay, if you take a look, this one should stand out, that this is probably going to be the one for heterozygous. So 2PQ, that's what you would use to determine what % of the population is heterozygous. P squared, well, we learned P up here is for the dominant. So P squared is going to be for what? Think about that for a moment. Homozygous dominant, right? So if you plug in a number here, you'll get what percentage of the population is homozygous dominant. Finally, the last one over here is Q squared. If you plug in there, you would get what percent of the population is homozygous recessive. Okay, and if you had to actually calculate this, you'd be given numbers like P equals 30%. Okay, so if you filled it into this equation here, we would find that P equals 0.3 plus Q equals 1. Well, the only possibility for Q is going to be 0.7, and that would equal 1. So when you fill in these numbers here, you'd go 0.3 squared, and that would be the percentage of the population that's homozygous dominant. 2 times 0.3 times 0.7 would get you the percent of the population that is heterozygous. And then finally, if you plug in 0.7 here, that would get you the percent of the population that is homozygous recessive. All right, now Hardy-Weinberg equilibrium is useful for calculating the percentage of the population for allele frequencies and all that stuff, but in reality, it's impossible for all 5 of those conditions to exist in a population. So here we're looking at the disruption of equilibrium. What does it take to actually change a population? Because remember, Hardy-Weinberg was never changing the population. So here, if we take a look, there are mutations. Mutations are occurring all the time. Okay, mutations are a natural part of change. So mutations occur in populations all the time. Gene flow, remember there's immigration and emigration all the time. So organisms don't stay in one place, they usually move in and out of populations. Genetic drift, we're going to talk about this in class. But basically, one of the conditions, number 3, it was that the population had to be large. Not all populations are huge. Some populations are very small, where they have only a few hundred individuals, such as, remember, the tiger, only 300 individuals in the wild. So we know not all populations are large. There had to be random mating, but out there in nature, a lot of the times females get to choose their mates. For example, in birds, females choose the mates with the brightest colors or the best song. There's deer, the ones that fight, with their antlers, and the ones that win, those are the ones that the females go with. Same thing with like buffalo and stuff. So females actually choose, they don't randomly pick their mates, they actually choose the ones that they feel the best. And finally, natural selection is always occurring. Okay, so I'm going to show you examples of 3 patterns we see in natural selection. So 3 types of natural selection, basically. All right, so the first here is directional selection. This is where there's a change in the environment, and the bell curve is going to shift in favor of one of the extremes. Okay, so here, let's say we're talking about beak size. And let's say we're on an island where the environment changes and all that's available is large, hard seeds. So before, we used to have beak size. So small beaks, medium beaks, and large beaks over here. Okay, and the average, this dotted line represents the original in the population. So the average, you had these medium-sized beaks, right? Well, then the environment changed, and as a result of that, the birds with the bigger beaks, even though there wasn't very many of them, they had the best chance of survival, while the other guys over here died off. So the bell curve shifts. Now having a bigger beak was better, so now we find more birds with bigger beaks in the population. These guys have died off, they're gone. The medium-sized ones, well, they could still survive, but there's far fewer of them than there used to be. And you can bet on it, there's going to be birds with even bigger beaks now. Okay, so our bell curve has shifted. It favored the birds with the bigger beaks here. Now they have become the average. There's more birds with that beak size.